For a fraction of a second, the moon blinked. It wasn't subtle if you knew where to look. A small, sharp flash appeared on the dark side of the lunar surface, then vanished. No sound, no debris cloud, just a pinpoint of light, captured live by a telescope on Earth and time stamped down to the millisecond. That alone is strange. The moon feels permanent. It hangs there night after night, unchanged like a background object. We don't expect it to do anything. And yet, in that moment, something hit it hard enough to release a visible burst of energy that travelled all the way to our cameras. What makes this different from the countless impacts that have shaped the moon over billions of years is that this one didn't happen in deep time. It didn't leave only a crater for future scientists to puzzle over. It happened now, while we were watching. For decades, astronomers assumed most small lunar impacts went unnoticed. They were too fast, too brief, too faint. But improvements in cameras, timing software, and coordinated observing networks have changed that. Today, a flash like this can be detected, measured, and analysed in real time. That changes the relationship. The moon stops being just a fossil record of ancient collisions and becomes an active sensor. A giant, airless target that reacts instantly when something crosses its path. When that flash appeared, it raised an immediate question. What exactly just slammed into the moon, and how did it get there? Because whatever it was, it didn't miss Earth by much. The first question everyone asked was simple. Was this a meteor, or was it something we put up there? The moon gets hit constantly by natural debris. Pebble-sized meteoroids slam into it at tens of kilometers per second, releasing brief flashes of light. Most are too faint to see, but occasionally one lands hard enough to stand out. That alone would not be surprising. What made this impact different was its timing and its predicted location. In the days before the flash, orbital analysts had been tracking an object with no propulsion, no guidance, and a slowly decaying path around Earth. It wasn't behaving like a natural asteroid. Its orbit was too tidy, too Earth-centered. That narrowed the possibilities fast. The leading suspect became a spent rocket stage, likely left over from a past mission, drifting through space for years after its job was done. These objects are common. Every launch leaves hardware behind, and some of it escapes into long, looping orbits that can eventually intersect with the moon. Teams working with data from agencies like NASA and European Space Agency compared the predicted impact window with the exact moment of the flash. The match was close enough to rule out coincidence. That doesn't mean the identification was instant or absolute. Space tracking is messy. Objects fragment. Orbits shift under the influence of sunlight and gravity. But when the flash timing, brightness, and location line up with a known piece of space junk, the odds tilt heavily in one direction. If this was human-made hardware, it means something we launched years ago finally came home, just not to Earth. And that realization reframes the event. This wasn't just a random space rock, it was a visible reminder that our activity around Earth now reaches all the way to the moon. Catching a lunar impact sounds harder than it is, but only because the moon does some of the work for us. There's no atmosphere up there. When something hits Earth, most of the energy is spent tearing through air, producing a streak of light that spreads out and fades. On the moon, all that energy dumps straight into the ground. Rock vaporizes instantly, heating up enough to glow for a split second. That glow is the flash. Modern lunar monitoring systems point telescopes at the dark portion of the moon, where even a brief spark stands out clearly. High-speed cameras record dozens or hundreds of frames per second, each one time stamped with atomic clock precision. Software scans those frames for sudden spikes in brightness that last only a few milliseconds. One camera isn't enough. Cosmic rays can strike a sensor and fake a flash. Satellites can pass through the field of view. Even electronic noise can mimic a signal. So observers rely on redundancy. Multiple telescopes in different locations watch the same region at the same time. If they all see the same flash in the same spot, it's real. Once confirmed, the brightness of the flash tells scientists how much energy was released. From that, they can estimate the mass and speed of the impactor. Not precisely, but close enough to sort a grain of sand from a chunk of metal. What's surprising is how routine this has become. These systems now catch dozens of impacts every year. Most never make headlines. They're logged, measured, and added to growing databases of lunar collisions. But every live detection is a small technical triumph. It means we're no longer just studying scars left behind. We're watching the moon react in real time, acting like a giant detector for whatever happens to wander too close. At first glance, a tiny flash on the moon doesn't feel important. Nothing broke. No one was in danger. The moon didn't even notice. But scientifically, these impacts carry a lot of weight. Every confirmed flash becomes a data point. The brightness tells researchers how much energy was released. Combine that with how often these flashes occur, and you get a clearer picture of how much material is moving through the Earth-Moon system right now. That matters because our models of space debris and small meteoroids are still full of gaps. The moon helps fill those gaps. It's a clean target. No weather, no erosion, no atmosphere to blur the signal. When something hits it, the physics are straightforward. That makes the moon a natural laboratory for testing impact models that are much harder to validate on Earth. There's also a practical side. Plans for long-term human presence on the moon are no longer abstract. Future habitats, landers, and surface equipment will sit exposed. Knowing how often objects of different sizes strike the surface helps engineers design shielding that's heavy enough to protect astronauts but light enough to launch. If the impactor turns out to be human-made, the lesson goes even further. It means old hardware doesn't just vanish when missions end. It keeps moving, sometimes for years, sometimes on paths that intersect with places we plan to return to. So that brief flash becomes a warning and a tool at the same time. It reminds us that the space around Earth is active and crowded, and it gives us a way to measure that activity with surprising precision. Nothing dramatic happened on the moon that night, but our understanding of the space around it quietly improved. The flash itself is only the beginning. After that moment is logged, the slow work starts. Orbital predictions give scientists a rough idea of where the impact occurred, but rough isn't enough. Over the following weeks and months, high-resolution lunar orbiters scan the predicted region, looking for something new. A fresh crater a few meters wide. A subtle change in reflectivity. Anything that wasn't there before. If a new crater is found, it can often be matched back to the flash. The size of the crater helps confirm how energetic the impact was and whether the original estimates were right. This feedback loop tightens the models and makes future predictions better. These events are also shaping how space agencies think about debris. Objects that once seemed harmless drifting far from Earth can still end up somewhere important. As lunar traffic increases with more landers, orbiters, and surface missions planned, that matters more than it used to. There's another shift happening too. Lunar impact monitoring is becoming more automated and more global. Amateur astronomers now contribute useful data alongside professional observatories. A network of small telescopes spread across continents can outperform a single large one when it comes to catching brief, unpredictable flashes. That means detections like this are likely to become more common, not because space is suddenly more dangerous, but because we're finally watching carefully enough to notice. The moon hasn't changed. Our attention has. And once you start seeing these impacts in real time, it's hard to go back to thinking of the moon as still and untouched. For most of human history, the moon felt distant and untouchable. A symbol. A calendar, a constant. Seeing something hit it live changes that feeling in a quiet way. It reminds us that the moon isn't frozen in time. It's part of the same moving, cluttered environment we're navigating around Earth. Objects pass through. Some miss, some don't. That single flash collapsed the distance between here and there. It turned a familiar object into an active place, reacting instantly to events we can measure and understand. Not millions of years later. Now. It also forces a bit of self-awareness. Some of what reaches the moon didn't start in deep space. It started on launch pads on Earth. Our exploration leaves traces, even when we're not looking for them. As we plan to return to the moon and stay longer, moments like this matter. They sharpen our models, improve our designs, and quietly remind us that space doesn't stop being dynamic just because it looks calm. The moon didn't change that night. Our relationship to it did.